Greetings and welcome back. Today we're going to be looking at a second video that has to do with Lewis structures. We're going to consider formal charges. It's really important to point out that formal charges are rare, but they're very important. So what we saw in the last video, where carbon makes 4 bonds, hydrogen makes 1 bond, nitrogen makes 3 bonds, that's the common thing to know. Hopefully you recognize both of these. These are the periodic tables from last video. The one on the left is the one that you will see hanging up in the corner of the wall of the classroom. The one on the right is a expanded version, just kind of focusing on the elements that we'll see mostly in our class, the nonmetals. All right, speaking of nonmetals, so you might remember from general chemistry that bonds are divided into 3 different types based on electronegativity. So let me give you 3 different examples. One would be hydrogen attached to hydrogen. One would be sodium attached to chlorine, and one would be hydrogen attached to chlorine. So when we look at these bonds, all of these appear to be covalent bonds, but really only 2 of these are covalent bonds. The one on the left is a covalent bond. It's truly a nice covalent bond. I'll write that out for you. And this is just what we were talking about last video, which is that covalent bonds are made when electrons are shared in between 2 nuclei. So these electrons right here are in the valence shell of the hydrogen on the left and the valence shell of the hydrogen on the right. They're covalent. They're valent to both of those guys. Looking at that second atom, or compound, sorry, sodium chloride doesn't actually make a bond. Instead, as you may recall, it is Na plus attached to Cl minus. So this is actually very incorrect, and I would never draw out NaCl with a bond between them. Hydrogen attached to chlorine, on the other hand, is still a covalent bond, but it's a covalent bond with an asterisk. The deal with this covalent bond is that the electrons are not evenly shared between the hydrogen and the chlorine. And it's actually the same reason that electrons are not shared nicely in between sodium and chlorine either, and that is electronegativity. So electronegativity is a property of elements that has to do with how much they like electrons. There's 2 parts to this. One is how much do they like to hold on to their own electrons, so how unwilling are they to share, and also how much do they want to steal electrons from other atoms, from other elements, and so that's their desire to steal them away. And electronegativity is a trend that is low on the bottom left corner and becomes very high in the top right. All right. The noble gases are very happy the way they are. So those don't actually count. They don't actually have electronegativity. But in general, what we see is, looking at this chart on the right, that sodium, magnesium, lithium, beryllium have very low electronegativity. And fluorine is kind of our king of electronegativity. This has the highest electronegativity. The general trend for these guys, and the ones that we're going to look at the most in class, is that carbon and hydrogen are about the same, and then nitrogen is next, and then oxygen, and then the halogens. So therefore, it's really low starting on the bottom left and high going to the top right, but since most of the things that we'll be looking at in this class are within the same row, consider it being low on the left side, high on the right side. And this should hopefully makes sense as to why sodium has a plus charge. It has very low electronegativity. It doesn't really actually like its own electrons, and therefore it tends to give them away. Chlorine, which is over here on the right side of the periodic table, has a very high electronegativity, so it actually likes to take electrons from other things. And so that's why sodium and chlorine in nature, when we find salt, when we mine it up or extract it from the sea, is found as Na plus and Cl minus. If you think back to last video, we talked about the fact that sodium would have 1 valence electron. It's in column number 1. And chlorine would tend to have 7 valence electrons because it is in column number 7. However, They don't exist that way. This would be only if they were making a covalent bond, but they don't make covalent bonds. So what happens instead is we take that one electron from sodium and move it over to chlorine. Sodium would have one fewer electrons than it should, which would be a plus charge on the sodium because electrons are negatively charged. So let me say that again. Electrons are negatively charged, so if you lose a negative charge, you become more positive. Chlorine, on the other hand, accepts an extra electron, and if you accept an extra negative charge, you become more negative. So chlorine here has 8 electrons instead of 7. It should have 7. It's in column number 7 of the periodic table. So one extra electron means that it would be negatively charged. And that's formal charges, which is really important and what we'll be moving into later on in this video. All right, but this is called an ionic bond right here. An ionic bond is just made up of 2 ions that are attracted to each other. So for instance, a plus charge and a minus charge would be attracted to each other. With the covalent bond, nobody has a charge because electrons are just shared nice and evenly. This would only happen between 2 hydrogens, or 2 nitrogens, or 2 oxygens, or 2 fluorines, or 2 chlorines, and it also generally happens between a carbon and a hydrogen. These are covalent bonds, and furthermore, we call them nonpolar covalent bonds. A dipole, which means when something is polar, think about the North Pole and South Pole. That's when we're talking about a charge disparity. So something is more positively charged and something is more negatively charged. It's because in a hydrogen-hydrogen bond or in a carbon-hydrogen bond, the electrons are shared nice and evenly, then nobody has more than the other, and therefore these electrons are shared nicely and evenly and there are no charges. An ionic bond is an extreme example where instead of the electrons being shared, they're completely on one side or completely taken away from the other side. Therefore, we see something with a full negative charge or a full positive charge. So these are exceptions to kind of that Lewis structure stuff where halogens don't always make one bond. Sometimes they make 0 bonds. Sometimes they make 2 bonds. And when they do that, they're actually possessing the wrong number of electrons, wrong being the, according to our Lewis structures, they should be making 1, but instead they're making 0. And that results in them having a formal charge. Or if you're into causativity, it's because it's having a charge, because it's got 1 extra electron, is the reason that it doesn't have to make a bond. All right, so where does that leave HCl? You may recall that we talked about how electronegativity is low on the left side, so hydrogen doesn't pull very hard on electrons. Chlorine, on the other hand, is very far to the right side of the periodic table, therefore it does pull very hard on electrons. So this does make a covalent bond. HCl does make a bond, but the electrons are being pulled very hard to the chlorine and very much away from the hydrogen. So they're being shared, but they're being shared unfairly. The chlorine has an extra kind of amount of those electrons. So sometimes we'll indicate that with a lowercase delta and a minus, the hydrogen with a lowercase delta and a plus. Lowercase delta is a change, so there's a small change in the charge of chlorine. Chlorine is a little bit more minus because it has a little bit more electron density. Hydrogen is a little bit more positively charged because it has a little bit less electron density. Another way to write this is an arrow with a little plus on one side, pointing in the direction to which the electrons are being hogged or stolen. And so we call this a polar covalent bond because there is a dipole. There is a disparity in charges. The chlorine has a little bit of minus and the hydrogen has a little bit of plus. Polarity is really important. Hopefully you remember a little bit from last semester. If not, we'll learn a lot more about it this year. But it's something we'll talk a lot about in lab, and it is actually kind of one of the root causes for reactions, is that when electrons aren't shared very evenly, someone has too many, someone doesn't have enough, and they are probably going to be relatively reactive molecules. And I'm going to be good, and I'm going to fill in my lone pairs around that chlorine. All right, so let's move into talking about how we can locate formal charges. We already saw the example of sodium chloride, which was Na and Cl looking like this. But let's also look at an example with this molecule right here, which is dimethyl ether. All right, so here's how we assign formal charges. A formal charge for any atom in any molecule is equal to the number of electrons that it should have, or the number of normal valence electrons. All right, so and should have comes from looking at the periodic table. And we subtract from that the number of bonds added to the number of unpaired electrons. All right, and what that gives us is a number, and that's the formal charge. So for instance, let's consider that sodium up there with no electrons. So the formal charge for sodium would be equal to the number of valence electrons it should have, and if you look at the periodic table, you would see that that is in 1 because it is in column number 1, minus the number of bonds. So it has 0 bonds, and it also has 0 unpaired electrons. So this would be 1 minus 0, which is equal to 1. Therefore, the charge of sodium, way up here by itself, would be a +1, or just a plus. For chlorine in NaCl, the formal charge is equal to the number of valence electrons it should have, which for chlorine is 7. It's a halogen. It's in column number 7. And when we subtract this out, it is making no covalent bonds. So this term right here, minus, and this would be 0, but it has 8 unpaired electrons around it. So you can see that there's 8 little dots unpaired around it. By paired, I mean paired electrons are shared electrons or bonds. So 7 minus 0 plus 8, or 8. So 7 minus 8 is -1, and therefore that's how we would solve that chlorine has a -1 charge. All right, so what about this carbon right here? That carbon, all right, and we'll kind of take this guy down here. For this carbon alone, and it doesn't mean for every carbon, but just for this specific one, the formal charge is equal to the number of valence electrons it should have, which for a carbon is 4, minus, it is making 4 bonds, and it has 0 unpaired electrons. So 4 minus 4 plus 0 would be just 4 minus 4, which is 0. What we have thus calculated is that that carbon has 0 formal charge, and so we wouldn't put a plus or a minus. It's just neutral. As a hint, everything we did in the last video gives us a 0 formal charge. So carbon by itself wants to make 4 bonds. If it's making 4 bonds, it's always going to have a formal charge of 0. Likewise, oxygen up here is making 2 bonds. If you recall from last video, oxygen should make 2 bonds, and therefore we don't even need to do this algebra. It has a formal charge of 0. Hydrogens with 1 bond, they all have a formal charge of 0. 99+% of the time, what you'll see in organic chemistry is carbons with 4 bonds, oxygens with 2, hydrogens with 1 bond, nitrogens with 3. And in all of those cases, get used to those numbers because those have formal charges of 0, and you don't need to worry about it. The times when we do need to be concerned is when we see things making the wrong number of bonds. So I will draw a molecule for you here in which oxygen is making the wrong number of bonds. So hopefully you'll note oxygen should be making 2 bonds. Carbon should be making 4 bonds. So if we look at our carbon, this carbon is making 4 bonds. We don't even need to check that guy. This oxygen is making 3 bonds. So it's making the wrong number of bonds, and we need to calculate out its formal charge. So the formal charge for that oxygen right there is equal to the number of valence electrons it should have, which for an oxygen is 6, minus the number of bonds, and that oxygen you might note is making 3 bonds. It has 1 to the left, 1 to the bottom, and 1 to the right. So 6 minus 3 plus, and then it has 2 unpaired electrons on the top. So 6 minus 3 plus 2, 3 plus 2 of course is 5, so 6 minus 5 is equal to 1, or positive 1. So therefore that oxygen has a positive charge because it has, really what it has is 1 less valence electron than it should, but where you can just calculate it out from the formal charge is that it should have 6 valence electrons. Instead it really has 5. So 6 minus 5 is +1, therefore we have a charge of plus. All right, so let's see how you can do on this. So just like we did last video, I'd kind of like to go back to this and say, what are we going to commonly see? Do we have to calculate this every time? My answer would be that you don't have to calculate this every time. So let's look at kind of our common players. Hydrogen should have one valence electron, so it tends to make 0 bonds. So this is with no charge. We're just going to make a little table right here. So with no charge, hydrogen makes 1 bond. Carbon makes 4 bonds. Nitrogen, which has 5 valence electrons, makes 3 bonds and has 1 lone pair. Oxygen has 6, so 2 lone pairs, and it makes 2 bonds. And finally, the halogens make 1 bond and have 3 lone pairs. So that's what we saw last video. That's the no charge. That's the normal situation. All right, so what happens when they have a plus charge? A plus charge means that they have 1 fewer electron than normal. So therefore, hydrogen, instead of having 1 electron, would have 0. So hydrogen would have 0 bonds. So an H plus is just a hydrogen by itself with no electrons. A carbon with a plus charge would mean that it has 1 less electron. So instead of having 4 electrons, it would have 3. And so therefore, it makes 3 bonds and then has no lone pairs. It actually doesn't have a full octet. So a C plus makes 3 bonds instead of 4 and has no lone pair. Nitrogen, if we take 1 electron away, well, we just take 1 electron out of the lone pair, and therefore an N plus would be a nitrogen with 4 unpaired electrons. Therefore, it would make 4 bonds and have a plus charge. Oxygen would, just like the example on the last slide, have 3 bonds and 1 lone pair. Again, you can go through and calculate these out. We did that on the last slide for the oxygen with 3 bonds and 1 lone pair. But this is what we get used to seeing, is these guys have the wrong number of bonds. Instead of having 2 bonds, oxygen with 3 bonds has a plus charge. And lastly, and this will be the rarest one on this whole slide, a halogen that has a plus charge would actually have 6 valence electrons instead of 7. So just like a normal oxygen, it would make 2 bonds and have 2 lone pairs. I cannot stress that that is very rare. Hopefully you can see why, because halogen is our most electronegative element, so giving its electrons away is not something it likes to do. All right, so a minus charge means that something has 1 extra electron. So instead of having 1 electron that it would share to make a bond, hydrogen with a minus charge means that hydrogen has an extra, or it has 2 electrons and it has a negative charge. Carbon, instead of having 4 electrons, would have a 5th, and therefore it would make 3 bonds and have 1 lone pair. So a C minus also makes 3 bonds, the same as a C plus. The major difference is that C plus comes from a carbon with 3 unpaired electrons and 1 pair. Carbon with a plus charge comes from having 3 unpaired electrons and no pairs. So carbon with 4 electrons makes 4 bonds. Carbon with 3 electrons makes 3 bonds and has no lone pair. Carbon with 5 electrons makes 3 bonds and has a lone pair. So that one's a little bit tricky, but again, you need to keep track of your lone pairs, draw them in, and you'll see where they go and where they don't go. All right, so nitrogen. Nitrogen normally has 5 electrons. A minus charge means it has 1 extra. So instead of having these 5 electrons, we would add 1 extra in, and now it would only make 2 bonds and have 2 lone pairs. So that's what a negatively charged nitrogen looks like. And oxygen, instead of having its 6 electrons, and oxygen with a minus charge would have a 7th electron, and that would have a minus charge. And note that there's only 1 unpaired electron, so it would make 1 bond. Lastly, and we saw this one already, a halogen should have 7 electrons, or neutrally it would have 7 electrons. But if it had a minus charge, it would mean it has 1 extra, and therefore halogen with a minus charge makes no bonds because it has a full octet. So I wouldn't say to memorize your way through these, but these are things that you should get used to seeing. There's actually not a lot of formal charges that we're going to need to worry about in this class. These are the only 10 that we really deal with on a consistent basis. And even then, the most common ones for us to see are going to be really an N plus and an O minus. Those guys are the formal charges that show up a lot. All of the other ones are possible, but not very likely. The most likely ones, again, that we're going to see all the time are when things have 0 formal charge. So hydrogen should make 1 bond, carbon should make 4, nitrogen 3, oxygen 2, and halogen 1. All right, so I'm going to give you one more problem on this. And again, I hope that if you have any questions, you will bring them to class. And as the last time, I will remind you of this. Please practice the problems, not just the ones that have been in this video, but the ones that are assigned under this video on the Canvas page. Try as many of them as you can. Bring any questions you have to class. We'll go through as many as you need to. But if you guys are all good on these basic questions, then we can move into kind of some medium difficulty questions, which will be the ones that are the kind that you'll be quizzed on. So have a great day, and I'll see you soon.